Section 3.4 is all about the continuity of functions, and we've already talked about functions being continuous or discontinuous when we looked at limits, and we talked about how when you look at both sides of an x value, if the function doesn't come to the same place, then the graph is not continuous. So let's just look at some. Here's a continuous function, the red line. There's no breaks, no jumps, no holes, no asymptotes. Now, if there's a vertical asymptote, what we describe that as being as an infinite discontinuity. If the function jumps from one function to another function, we call that a jump discontinuity. If there is a hole, we would describe that as being a removable discontinuity. And there are three continuity principles that have to be met in order for something to be considered continuous. First of all, the function must exist at that point. Second of all, the function must have a limit at that point that exists. And those two values have to be the same. The function's value and the limit have to be the same. So let's consider question 1 here. If we put -1, we see that there would be 0 on the bottom. That would make it a vertical asymptote at -1. We would call that infinite discontinuity. In question 2, when we say the value of 1, if we put 1 into here and into here, we find that there is a hole at 1. Now what we need to check though is that because the value is 2 at 1, we need to check that when we simplify that we don't end up with the same value of 2 because that hole would be filled in. In this case though, that is not the case. When we replace x with 1, we get 1 plus 4, which is 5. So for this graph, it would be a linear function going through 4 with a positive slope. But at the point 1 and 5, there would be a hole. There are some functions that are always continuous, and you can write them on your cards. And you can see them right here on this page, that there are constant functions, polynomials, powers, roots, some trig, some exponential, logarithms. They're continuous. And sometimes even when you combine them together, they're continuous. And so the big thing is we got to be able to graph. And let's take a look at this example and talk about why they're not continuous. At 4, we're going to have a vertical asymptote, and we would say that's not a continuous situation, because when there's a vertical asymptote, we call that infinite discontinuity. At x equals 1, on one side of 1 we have, it looks like a quadratic function or a rational function. On the other side it's linear, and they don't come to the same place. There's no limit at 1, so therefore it is not continuous, and that would be a jump discontinuity. At -1, we have ourselves a hole, which is a removable discontinuity. And at -3, there's another hole, which would be a removable discontinuity. It's not continuous because although the limit exists, the function is not defined at that point. So to deal with these questions, you got to be able to deal with domain, range, and graphing, and all kinds of stuff. So if you look at this complicated function, what is the domain of this function? And you can see there's a problem with the root that 9 minus x has to be greater than or equal to 0. So when we solve for x there, x has to be less than or equal to 9. So when we start graphing this less than 9, let's go ahead and put 9 in. We're going to get 9 squared, which is 81 minus 4 times 9 is 36. So 81 minus 36 is 3 to a really big power. It's going to be really large. And as the values get smaller, what is it going to look like? Well, do we really want to go through that? What type of functions are these? We have a combination here. This is a root function and a power function. And we just said a few pages ago that those are always continuous, and combinations of them are continuous as well. And the only time we run into problems is that when we have this, that there is an undefined situation, or if it's a, what do you call it, the piecewise function, then we might end up with a jump. What about this question? Where is it discontinuous? We would say, well, it's discontinuous. X can't be 5. And if we put 5 in because it's indeterminate at 5, so I'm going to find the function's value at 5. After we cancel out the x minus 5, you're going to be left with x squared plus 5x plus 25 when you do SOAP on the top. And when we replace 5 with, or x with 5, we're going to get 25 plus 25 plus 25, which is 75. We then need to check and see, well, what's the limit as x approaches 5? Minus 5, pardon me. Ooh, that's not right. Because it's minus 5, not 5. And when I put minus 5 into there, I'm going to get just 25. What's the limit as x approaches minus 5? Well, we would end up with the same kind of situation when we factor. Right here, and we still get 25. If we looked at it from a graphical point of view, we have ourselves a quadratic function that opens up that doesn't cross the x-axis. That crosses at 25. And at minus 5, there's a hole in the graph, so it would be way up here somewhere. And the actual value of that, when we put minus 5 in, is 25 seconds wrong. Anyways, I will have to deal with that another time. But you get the picture. We have to be able to picture a graph in order to talk about the discontinuity, and you're going to have some trouble, especially with these absolute value ones, and we'll do some of them together. Here's the assignment, and we'll work together to get through this, and then we're done chapter 3, and we'll be moving into chapter 4 before you know it.